Okay. All right. So one lesson today on what is called electrochemistry. It'd be nice if I had a few more. Electrochemistry is a very important topic in chemistry. Let me just define what electrochemistry is here in a moment on the second slide, and then I'll talk in a little more detail about why electrochemistry is so important. The text reference is not a big deal. I don't know if anybody's really used their text. By the way, let's bring those textbooks back in maybe next week sometime. I don't know if anybody's unless you're using it to study. I'll just put it on the shelf there if you've got it. And again, yeah, we'll just get those gathered up. Anyway, the text reference is there, but it's not that important. Okay, so what is electrochemistry? We've got a very simplified definition here. It involves the reactions of metals and nonmetals. And it's really about ions, ions becoming atoms, and atoms becoming ions. The conversion of chemical energy into electrical energy, and that's the big part of it. So right now we all use many electronic devices. You know, we all have cell phones, smartphones, whatever you want to call them anymore. And they work based on battery technology. So you probably have encountered a phone that somebody's battery doesn't last very long. You say, that's terrible, my battery sucks. Certain phones maybe last a little longer than others. And this is all due to electrochemistry. So battery technology is all about using chemicals to create electrical energy. We've probably maybe noticed in the news examples of battery technology failing. These hoverboards, they're calling them. They got the two wheels on them, right? And you stand on them, and they're bursting into flames when they charge, or maybe they're doing it when they discharge too, for all I know. That would be an error with the battery technology not being able to handle the amount of charge that's needed to be, you know, added or removed, and overheating the battery. So battery technology is electrochemistry. The conversion of electrical energy into chemical energy. A process that takes a piece of metal, or perhaps a piece of plastic. It has to conduct in some way, and coating it with certain other chemicals, sometimes called electroplating, is also uses electrochemistry. So years ago, when cars had more metallic pieces on them, like a big chrome bumper, that bumper would have been made out of steel, which then would have been plated with chrome plated, all right? You can buy costume jewelry that is probably just made out of, you know, steel, out of just cheap metal, which then is plated with silver plated, all right? And that would use electrochemistry. The thing that's being plated would be placed into a solution. Electricity and electrodes would be put into the solution. Electricity would be put in, and the atoms would be plated to the object that you want to cover with those particular atoms. So electrochemistry is a very important process. It's also found in nature when a plant takes in. You're not going to watch anything back there, are you? Yeah, no, you're not. That's good. Don't be watching. Listen. So when a plant takes in sunlight, and that sunlight is used for photosynthesis, the plants, you know, the pieces of the plant, the chloroplasts, all those good things, they will do some electrochemistry to then change some of the molecules in there so that the energy is being stored in the molecules. Okay, let's do some examples here, because you can write down oxidation reduction reactions, but don't write down the bullet. So we're going to be talking about two processes, something called oxidation and the second one called reduction. And this is really the chemical reaction that takes place during electrochemistry. For short, it's sometimes called a redox reaction for reduction and oxidation. And we're going to learn how to, analyze a reaction using these terms. This is a single displacement reaction. If you place a piece of zinc metal into a solution of copper 2 sulfate, a single displacement reaction occurs and a fuzzy coating of copper forms on the zinc. All right, when we did single displacement reactions, I would have showed you copper and silver, and it would have made that nice kind of silvery, kind of glow, shimmering thing. And so oxidation reduction reactions are very significant in single displacement reactions. So let's do an example. So you can write down that particular reaction. Well, we're going to be doing a total ionic equation and a net ionic equation. So you don't have to write the titles down if you don't want, but you can. We've already done net ionic equations. So this is really kind of a review of something that we've done in the past. But we need to do this because in order to understand the oxidation reduction reaction, we want to get rid of the spectator ions. Remember, they're the ions that stay the same. They don't do anything in the reaction. It would be really cool if we had enough experience in this in order to see what the spectator ion is. I don't think we necessarily can. That's why I'm going to write it out. But does anybody maybe want to take a guess? Which of those ions is not changing in that reaction? Which of the ions is the same on the left as it is on the right? And there is only one of them in there. There's one thing that doesn't change in that reaction. One of the ions. What do you think? What do you think there, Conrad? The SO4 is correct. The zinc starts as a hunk of metal, solid, and then becomes an aqueous ion. That's different. The copper starts as an ion and then turns into solid copper. Those are different. But the SO4 is an ion both times. So though that the SO4 is the spectator, so we could actually jump right down to the net ionic equation by getting rid of the SO4. Now I'm going to write it out so that you can see it, but we could go right to the bottom. We don't need the SO4. So Zn, and I'm going to put the 0 up here. And the 0 represents the fact that it doesn't have any charge. It's metal and it doesn't have a charge. It hasn't gained or lost any electrons. Next we've got the copper, and this is +2 when we break it apart from the sulfate. Next we have the SO4, and that's -2. Notice I'm getting rid of the AQs and the S's this time, because I don't really want to worry about whether it's solid or whether it's aqueous. I'm very much worried about the charge, because the charge is where the electro part of electrochemistry is coming from. It's the electricity part of it. Next, I'm going to have a copper. It's by itself, so it has a charge of 0. And we're going to have the Zn, which was bonded with the sulfate, which means it's a +2, because I'm doing the reverse charge. And I'm going to have an SO4, and it is -2. And as you can see, the SO4 is the same in both, and we will cancel out the spectator ion. And now the net ionic equation. So in other words, what is happening in this reaction? We have the zinc metal and the copper ion turning into the copper metal and the zinc ion. All right? And we actually did these types of reactions when we learned about single displacement reactions. We did some net ionic equations. Okay? All right. So now let's analyze this net ionic equation. And let's analyze it very closely. And let's take a look at what happens to the zinc and what happens to the copper. So let's change the slide. You don't have to rewrite net ionic equation. We have that. You have it in your notes. I just put it up there so that I can see it. So let's consider the zinc first. So what's happening to the zinc? Well, let's break the chemical reaction into two halves. We're going to pull out the zincs, give them their own chemical reaction, and we're going to pull out the coppers and give them their own chemical reaction. When we split a reaction into halves, they're called half reactions. So we're going to look at the zinc half reaction. Zn, zero charge, is becoming Zn plus 2, or 2 plus, it doesn't matter. Now, let's think about what happened in that chemical reaction. How does a zinc atom with a charge of 0 become a zinc ion with a charge of plus 2? What had to happen to that atom? How do atoms become ions? What do they do? Nope. There is energy involved, but we're talking about the particles that make up the atoms. What did the zinc have to lose to become a charge of plus 2? It's 2 electrons, all right? Because we can gain or lose electrons to become ions. So it's 2 electrons plus 2 electrons. Now, how do we know that it's 2 electrons? Well, just like any chemical reaction, a half reaction has to be balanced. And in order to balance the charge, if I have a charge of 0 on the left, and I have a charge of plus 2 on the right, I need 2 negative charges to balance the charge. So we have 2 electrons along with the positive ion. Now, this half reaction has a name. Its name is called, and I'm going to change the colors just because I don't want to get it confusing. This is the oxidation half reaction. It's the oxidation half. All right? Okay? So this is the oxidation half reaction. Whoops, thank you. Now I'm going to write a few more things underneath here, okay? But let's talk about now the copper half reaction. But I'm going to add a little definition in this spot. So let's look at the half reaction for the copper. The copper starts as Cu plus 2, and it is becoming Cu0. All right? And that half reaction also needs to be balanced. And I can only balance it with electrons, because electrons are the things that move around during chemical reactions. Where am I going to put the electrons in this reaction to balance out the charge? What side do the electrons have to go so that the charge on the left is equal to the charge on the right? Where am I going to put the electrons? It's going to go on the left side. I don't want to say first half because we're using half to describe reactions, but you're right. It's going to go on the left side. It's going to go on the same side as the positive ion. Excellent. So this is 2 electrons. Okay? So what happened during this chemical reaction? Well, the zinc 0 lost 2 electrons, and the copper plus 2 gained 2 electrons. This is called the reduction half. All right? It's called the reduction half. Now let's come up with a way so you can label one half as being oxidation or one half as being reduction. Oxidation, and this is where I'm writing it underneath, is when something loses electrons. It's a loss of electrons. It means the electrons are on the right, because the thing on the left lost its electrons. They're now separate from them. It's on the right-hand side of the chemical reaction. Okay? So oxidation means something lost its electrons. It became oxidized. Now, the term oxidation, you probably think with things like rusting. Something oxidizes, right? You might even think about it in terms of burning things. We call it oxidation sometimes when something combusts because it reacts with oxygen, because it has the word oxygen in it, right? And that's a historic name. Chemists, once they learned about the periodic table and learned about electrons, realized that when something like iron oxidizes and turns into rust, the iron atoms themselves are losing electrons because they didn't know about electrons when they first learned about oxidation, when they learned about rusting. So they would come up with all these terms to describe what was happening to things like iron. Oh, it's rusting, it's oxidizing because it's reacting with oxygen. But we now know as chemists that every time something oxidizes, the element we're talking about is giving its electrons away to the oxygen. So we now know that in general, in more specific terms, oxidation is when something loses electrons. And that's where the word comes from, okay? Reduction. Reduction is when something gains electrons, all right? We have a gain of electrons. So reduction is when a substance, an ion or an atom, gains electrons. In this case, the electrons are on the left of the reaction. Now, I really don't know where the term reduction came from historically. Oxidation, I just explained. There's one way I interpret reduction. It has to do with the charge number. Notice the charge number on the copper started as +2. And then when it gained electrons, because electrons are negative, the charge went down to 0. The charge was reduced in value. See how that works? It got smaller, it went down. Now, that doesn't work if you're talking about negative things. If negative things gain more electrons, they're going to get larger negative. In other words, they're still going to go down, right? So if you had a number line, when you gain electrons, you go down the number line, you reduce the value. So that's the way I interpret reduction. But it's when something gains electrons and its charge number goes down, it becomes reduced. Okay? So, oxidation half, the electrons are on the right, this thing lost electrons. The reduction half, the electrons are on the left, this thing here gained electrons and was reduced. Okay? All right. How do you remember, gaining electrons is reduction and losing electrons is oxidation? There's two ways in which you can do this. Here's one little, oh, wait a minute. Oh, let's jump ahead. Two ways in which you can help yourself remember. So if you can remember the term oil rig, oxidation is loss of electrons, reduction is gain. So that's a way to memorize what the gain or loss. Now that's for the benefit of all you petroleuites here. We got to relate it to oil. That's part of the curriculum requirements. But for those of us that grew up out in Watford, like myself, my chemistry teacher said, Leo, the lion, says, grrr. That's the way I learned it. So what do you think Leo stands for to help us remember about oxidation and reduction? What does Leo stand for, you think? Loss of electrons, oxidation. And grr, reduction. Gain of electrons is reduction. There you go. So, whatever your, your geographic position is, if you like live close to Petrolia, Inwood, you can go both ways. Inwood, you're just right on the line there. Shetland? Does anybody live in Shetland?
I live like 5 minutes out.
Like that's out there. We don't have anything for you. You're lost cause. You might as well be in Euphemia, for crying out loud. Oh yeah, see, there you go. Yeah, there's no help for you. Sorry about that. Wyoming, yeah, you're Petrolia, so you're oil rig. Yeah, actually, I'm just joking. It doesn't matter which one you learn. Everybody understands that, right? Okay, so that's just a helpful way to remember it. Now, I'm going to go back to the previous slide, because the previous slide, I think we've covered all the information we need on the previous slide. Let's not write this down. Oxidation is the loss of electrons. We've already wrote that down. In the above reaction, blank was oxidized. Well, let's go back to our half reactions here for a moment. In the above reaction, this is the oxidation half. So in the above reaction, zinc was oxidized, right? So it's the reactant that is oxidized. So again, on our next slide, which I'm not going to have you write down because we've already talked about it, it's the gain of electrons. We wrote that down. That's what reduction is. In the above reaction, all right, which one of these things was reduced? Which one of those chemicals on that screen was reduced? Copper plus 2 was reduced. So it's the reactant, right, that was reduced. Okay? Now, 2 more definitions, and then we'll do a few more example problems, and then I'll let you kind of work away. So let's write down the 2 definitions, and then we're going to come back. So if you could write those 2 things down, we will go back and take another look at this. And I'm not going to describe anything quite yet. I'm just going to let you write that. Leave some room here, because I am going to put another line with some information underneath here, underneath both of them. So just to make things a little confusing, chemists like to talk about a chemical that then allows for oxidation. The agent of oxidation. And we call that the oxidizing agent. So, like I said, chemists like to talk sometimes in terms of, what caused the reaction, and this is what this is. So an oxidizing agent is a reactant that causes or allows for oxidation. Now this can be confusing because if the thing is allowing for oxidation, it itself must be reduced. So we have to actually look at the reduction side in order to find this. Reducing agent, it's the thing that allowed for it's the thing that allowed for reduction to take place. And it's actually the thing that was oxidized. So let me now go back to our picture here, and let's talk about this. So in an oxidation reduction reaction, there always has to be two halves. You cannot just have one half existing by itself. You must have both of these reactants in the solution in order for the reaction to happen. And why is that? Because if something loses some electrons, there must be something there to pick the electrons up. The electrons just don't hang out there in the solution. It's not like they leave and then they're hanging there like on a, on the side of a street waiting for a bus. Gee whiz, I got nothing to do. The electrons, it doesn't work that way. Once these are dropping off their electrons, the copper is picking them up. They actually don't exist out there in empty space for any point in time. It's literally a trade. You take my electrons, okay, I'll take those electrons. So this reaction cannot happen without this reaction. They work together. So in this case, the zinc was oxidized. And it was the presence of the copper plus 2 that allowed the oxidation to take place. So the zinc was oxidized, and if it wasn't for the copper plus 2, the zinc couldn't be oxidized. We needed the other reactant. So what does that do? That makes, and I'm hoping that maybe you've got still some room under here, but we'll go back to the definition. The Cu plus 2, all right, is and it's an agent of some sort, and it allowed the zinc to be oxidized. So it's the oxidizing agent. All right. So it's the oxidizing agent. It allowed the thing to be oxidized. If it wasn't there, it couldn't be oxidized. So it makes it a little confusing. This is the reduction half. The Cu plus 2 was reduced, but that makes it then the oxidizing agent, because then it allows for the other thing to be oxidized. I know it's a little confusing, but we can memorize our way through it. Gain electrons reduction. The Cu plus 2 is reduced. Therefore, it's the oxidizing agent. It allowed for oxidation to take place. I can now do the same up above. I'm hoping to squeeze it in here. Therefore, Zn0 is the, what did the zinc allow to take place? What's that? It's the reducing agent. It allowed for the reduction to happen. If it wasn't there, the reduction couldn't take place. And therefore, the zinc 0 is the reducing agent. All right? And like I said, it's a little confusing because we're using the term oxidizing for something that's being reduced. But if it wasn't there, the thing couldn't be oxidized, so it's the oxidizing agent. All right, excellent. So we've plowed through that one. We did oil rig. We've defined oxidizing agent and reducing agent. Let's do some examples. First, let's define what a redox reaction is. So a redox reaction is all about trading electrons. and they go hand in hand. You can't have the half reactions happening by themselves. I think I got that point across just a moment ago, so I'm not gonna say it again. So you have to put them together in what we call a redox reaction or an oxidation reduction reaction. Now, before I do some examples, how does this turn into battery technology? Well, if I have both the reactants in one beaker, it's not a very good battery because the electrons are transferred inside the solution. But if I separate the two reactants, if I separate them in two beakers, and then I put some connecting tubes that allow ions to move, then I can get the chemical reaction to take place separately, and I can force the electrons to move through a wire. And if I separate the half reactions and force the electrons to move through a wire, then I can put a light bulb in the way of that wire, or I can put a cell phone in the way of that wire, or I can put a whatever in the way of that wire, and then I can run it. And that's the way a battery works. The half reactions are separated from each other inside the battery. There's a division in there, and the electrons are forced through an external circuit, and that's how the battery works. If we had more time, a couple more classes, we'd go into that detail, and I'd show you how the batteries work, and we would do a lab where we would make simple little batteries. It's kind of fun. We would use little voltmeters. We could measure it and do some stuff. But we don't have time, but that's okay. All right, so let's do some examples here. So in these examples, we're going to come up with the net ionic equation. We're going to write the half reactions. We're going to state what the reduction half is and the oxidation half. And we're going to state what the oxidizing agent is and what the reducing agent is. And really, my assignment is exactly this. That's the type thing that's on the worksheet, which I've turned into a brief little assignment to kind of make you do it. And the questions on the exam are all based on this. What's the reduction half? What's the oxidation half? What's the oxidizing agent? What's the reducing agent? So the first thing we need to do once you've got that reaction written down is get rid of the spectators. What ion in there does not change on the reactant side and the product side? What ion is the same? Ion that it doesn't change, yep. The NO3, correct. And so we can ignore it. So if we can go straight to the ionic equation, that'd be great. And I think we can do it. So the copper is solid. What charge goes on it if it's a solid? 0, because it hasn't gained or lost any electrons yet. 0 plus 2 Ag. Now, what's the typical charge of a silver? If you've got your periodic table, you can check. Or nitrate, if we check on the back, has a charge of -1. So it is +1. So it's plus. And this is turning into 2 silver solids. If it's solid, what's the charge? 0. And the copper is reacted with 2 nitrates. So if I do a reverse crossover, that's +2. So let's now break it into the half reactions. The copper's in one reaction and the silver's in the other reaction. I'm going to write it out and then we'll do some thinking here. So here we've got Cu0 becoming Cu +2. And I'm going to leave some space. I'm going to write the other half reaction, 2Ag plus becoming 2Ag0. Okay. Now we've got to place the electrons in order for the charge to be balanced. In this first half with the coppers, where do my electrons go? Tell me the side of the reaction to put the electrons so that the charge is the same. If I put 2 electrons on the left, which I'm not going to because I can't erase, I would then have a -2 over here, and I'd have a +2 over here, and that's not the same charge. It's got to go on the right side, because I have to bring this number down to 0, 2 electrons. I have to bring that charge down by adding negative charge. Where do my electrons go in the second half? Yep, on the left. And how many do I need? I do need 2, because I have 2 plus charges. So I need 2 electrons. Each silver is +1, but there's 2 of them. So I need 2 electrons. Then it would just be 1. Yep. But in this case it does, so I've got to have it. So let's start now defining and describing things. What half is this first one if the electrons are on the right? Oxidation because it lost it, and they're on the right. So this is the oxidation half. Excellent. With electrons on the left, it's reduction. It's the reduction half. It gained electrons, has it on the left. This reactant, if it didn't exist, it wouldn't be able to take place. So, Cu0 is which agent is the copper metal? Which agent is the copper metal? What did that copper allow to take place? It's reduction. It's the reduction or the reducing agent. So the thing that was oxidized allowed this other half to take place. So it's the reducing agent. If the copper wasn't there to give the electrons to the second reaction, that bottom reaction couldn't happen. It's the reducing agent. What's the oxidizing agent? Yep. Let's be more specific. Which version of the Ag? Because there's Ags in there. Ag positive. It's the reactant. Correct. Ag plus is and it's the oxidizing agent. All right? It has to be the reactant. That's what we're talking about. All right, excellent. That's the analysis I want you to be able to do. All right? I want you to tell me whether it's a reduction half or an oxidation half, and then I want you to tell me which agent is which. Let's do, I think, one more, and then I'll let you work. Can we get it? Understand it in one? Can we? I don't know, Amy. Are you sure? Because you screwed up that last answer. But now you get it. You think? Oh, you were writing a test. You came in a little late. Right. Okay. It's understandable. Okay, this one's a little tricky. Which of the ions is exactly, well, here, I'll let you write it down, because I do want you to write down the whole reaction before we get rid of the spectator. But again, we're thinking from the whole reaction, which of the ions is a spectator? We want to get rid of it. And then we'll break it into its halves. It's a gas, but that's okay. We're not afraid of that. Which of the ions is the same in this thing? Which is the thing that doesn't change? The hydrogen actually does change. We're guessing at this point. What's that? It's the chloride. The chloride doesn't change. It's chlorine, but it's the chloride. What's that? The hydrogen changes greatly.
No, but there's the 2 in front of the chlorine.
Ah, well, we might, it's aqueous. That's the key, right? That the chloride is aqueous. Even though there's 2 of them, there's a 2 in front. So there's 2 chlorides, it's the same. This is H2, and it's a gas. This is H plus, and it's aqueous. That's a different thing. One's a solid, and then the other one is aqueous. Those are different things. So you're right, it's the chlorides that are the same. So what do we have? We've got M, I wanted yellow. I got Mg0 plus 2H, and what's the charge on that H? It's H plus, because the chloride is negative. H plus, becoming Mg, what's the charge on that Mg with 2 chlorides stuck to it? Plus 2, and now I've got H2, and it's a gas. Now, just like the metals, the solids, all right, they have a charge of 0 because they're in their elemental state. That's the way we find hydrogen. Hydrogen's a Hofbrinkel gas. So for all of those Hofbrinkel gases, its charge is also 0. Because it's behaving just like the solid, except it's a gas. It's not a solid. So it's in its elemental state, H2, it's also 0. So if I had a Cl2, it would be 0. If I had an O2, it would be 0. Okay? If I had an N2, it would be 0. Okay, let's break it into their halves. Mg0 becoming Mg plus 2, 2H plus becoming H20. I'm hoping at this point you can add the electrons, and then you can determine the reduction and oxidation halves, and then hopefully you can determine the agents. So electrons are negative. They're going to bring charge down. You want to have the same charge on both sides. And you'll notice the charge on one side for both of them is 0. So you gotta take that charge down. So, first half, where do my electrons go? Bree, you got an answer? Where am I putting electrons in that Mg run? Where am I going to put them? What charge are electrons? They're negative. And I need to make the charge 0 at some point in time. So where am I going to put those negative charges? What side of the arrow am I going to put them so that everything is 0? Sorry, say that again. If I put -2 on this side, -2 plus 0 is -2, right? This side is +2. That doesn't make the charges the same. So where am I going to put my negatives to make the charges the same on both sides? On the right. Well, you had the benefit of the left being wrong, so Jess fires up the hand and gets the correct. That's correct. So +2 electrons. For the examples that I'm going to give you, there will only be positive charges on the ions. In more difficult questions, there can be negative charges, and then it gets a little tricky. But for the examples that you get, there will always be a 0 and a positive. That means the electrons always go with the positive thing to cancel out the charge. That's another way of thinking of it. The electrons will always go with the positive thing to cancel it out. Where am I putting the electrons in the bottom one? Yeah, Jess. Nice, good work. And how many? Nice, 2. Good job. It's my last video. I gotta get some fun, make some fun of some people here. It's like the parting show, right? So I gotta do a call. Everybody gets to be called out. John, right? That's correct, John. John. All right. Okay. So this side here, or this one here, what type of reaction is happening? What's going on here? I need a pen here to write with. The electrons are over here. This thing, what did it do to its electrons? Oil rig or Leo the lion, I don't really care. Oxidation is correct because it lost its electrons, or the electrons are on the right. Okay? So this is oxidation half. Oxidation half. And therefore, what is Mg0? It's the, Jess? Reducing agent. Reducing agent. Excellent. The reactant on the oxidation half is the reducing agent. It allowed for the other half to happen. Once you have one, by the way, you always know the other because they are opposites. It's that simple. But it is gaining, GER, right? Gain electrons, reduction. So this is the reduction half. No, you can remember Leo and GER, I'm pretty sure. That's why it's such a handy thing of saying. You could, oh, all right. So, which is the, and oxidizing agent. Which thing is the oxidizing agent? I'm going to pick on Felicia, right? This is my, like I said, this is my, because she's busy doing stuff on her phone and not paying attention. So Felicia, what is the oxidizing agent? H+, correct. Nice job. Big save. Big save. So Felicia has mastered it and has grown bored with my discussion, I believe is what the assessment is. What's that? Yes. Now I do have another example there, but it does deal with negatives. No, let's not bother with it. We'll stop right there, and I will now let you work on that worksheet, which I've turned into a little assignment. And it says there on the Google Classroom that I only want you, well, I want you to do them all, but the only ones I'm going to mark for numbers 2 and 3 are part A. So do it completely and correctly. All right? Okay? All right. So you guys can go ahead and work on it. And in actual fact, this example here has some negative charges, but I don't want to get into the negative charges right now. One of the examples I'm pretty sure on the sheet has negative charges in it. I'll tell you which one they are, and you don't even have to bother with it. You won't have to do it. Let me stop my recording here for a moment, and then I will take care of that.